How's it going, everyone? Sorry for the late video this week, but welcome to the 7th drill. Today we're going to be talking about repeated measures. Need to install 2 new libraries, most likely, unless you've installed them before. We got the Easy package and another one called LME4. The Easy it will be using for the repeated measures, ANOVA, and LME4 is a library for mixed effects models. That's a very popular one that we're just going to barely scratch the surface with, at least certainly for today. But we're going to have, as always, tidyverse will run LM support, Easy, and LME4. I've already run them, so they won't run. The reason that I have this select minus X1 or filter from this pipe is just if you just read this CSV file itself, you'll notice that there's a column called X1 that was just the row numbers that was left in there when this file had been previously exported, and we just don't need that. So this is simply taking that column that we don't need out. So the data that we're going to be looking at today, one other thing, you'll want to run this options digits equals 2. When we run the Easy ANOVA, it will give you some wild decimal places if you don't run that option, and this will keep the decimals reasonable. So the data set that we're going to be looking at today is called the Iguana data set. It has 3 variables: ID, sand, and extrusions. And in fact, I'm actually going to pull up over this because I just want to show, if you look at this, if we sort by the ID, then we can make very clear what's going on in this data. That we have we have 10 different iguanas, and each iguana has 5 different types of sand and some number of extrusions. And so iguanas are thought to stick out their tongues to sample the environment to detect, possible threats. And so these 10 iguanas are exposed to 5 different kinds of sand, 2 control conditions: their home sand and clean sand, and then the 3 treatment conditions, which are sand that's been exposed to fellow iguanas, sand that's been exposed to a different type of lizard, a competitor species, and then or kangaroo rats, which is another competitor species. So the number of times they extrude their tongue is counted to see if it varies across the environment. So that's the repeated measures design that we're going with today. So first, we could look at some descriptive stats. And the way that, of course, we know is, we just take our data frame, we pipe it in, we group it by those types of sand, and then summarize. We'll look at the counts, means, and standard deviations for each of those things. And we can see that, like the clean sand, on average, iguanas stuck out their tongues 6.8 times. The home sand was about 6, the iguana sand 7.4, K-rat 23.1, and lizard 9.4. So there is since today we're getting into the Easy package, there is a function called Easy Stats. And basically all of these Easy functions that we'll work on today have kind of the same setup, or at least very similar setups. Honestly, I don't use this library very much. As we'll talk about in a little bit, it's ideally suited for like real simple designs, but basically in these functions you'll just define different parameters depending on the design of your study. With your data, what's your dependent variable, what is the within measure ID variable. So if it's within subjects, then your within ID variable would be whatever your subject ID variable is. And then things like within listing what are your within variables, and then like what are your between variables, etc., etc. So with Easy Stats, if we just tell it our data equals df, within ID is that ID number, the within variable is sand, and that the dv is extrusions, and run that function, it will also give us the that n mean standard deviation plus this FSLD, which, in short, that's the Fisher's least significant difference statistic. So if you were treating this as a post hoc, test to see, and if you were using something as simple as Fisher's least significant difference, then you would say anything that differs by at least 6.9 points is, where the significant difference is. But keep in mind that that's more appropriate as a post hoc test, a follow-up test, because arguably if you don't have a main effect, then searching for differences between different things could be considered p-hacking sort of thing, and not great. So just ignore that FSLD for now, LSD. As far as running a repeated measures ANOVA for the inferential statistics that I'm talking about, it's basically set up the same way, but instead of easy stats, we're using easy ANOVA. And we set it up basically the same way. We tell it our data, we tell it our within ID variable for the subjects, we tell it our within variable, our DV is extrusions, and I'm going to add in one additional argument that is detailed equals true, and that's where it gives us the SS's. And when we run this, it runs our repeated measures ANOVA. Now, for this output, don't worry so much for now. We're going to kind of gloss over these the sphericity stuff. There are some assumptions with repeated measures ANOVA, or just with repeated measures, that we're not getting into yet. So for now, we're just going to pretend like this output isn't there. And what we're really looking at here is the ANOVA table of this easy ANOVA here. And so now we can see that for that sand, with 4 and 36 degrees of freedom, your F value is 8.8 and P is less than 0.05. So yes, there is a significant difference between the types of sand. But again, because this is an ANOVA, all it tells you in this omnibus test is, yes, a significant difference exists somewhere in these groups, but it doesn't tell you where that significant difference is. From there is where you could follow up with something like, Fisher's least significant difference, or whatever post hoc test. This, I would argue, is not the most rigorous follow-up test, but point is that if you're using the ANOVA framework, it is more appropriate to show that yes, there is a significant difference, and then you can go into probing those where that difference is. But then again, that is one of the reasons that I prefer linear modeling, just categorically, and I don't use any sorts of ANOVAs personally. Rather, I design my studies with like planned contrast in mind, to be clear. And so then finally there's Easy Plot, which is another easy package, and again, it kind of set up the same way. The only difference is now we have this argument of telling it what we want on our x-axis, which is that sand variable. And so when we run Easy Plot, we will get a quick plot of these means. If we were to compare this repeated measures ANOVA, and this I say to note this F test here on our ANOVA, this F of 8.8, P is less than 0.05, and 4 and 36 degrees of freedom. So noting that, now let's look at model comparisons. And before we look at the right way of doing things, let's look at the wrong way of doing it, which is ignoring that non-independence. And so just to be absolutely clear, the reason that there is independence in this data is because all 5 of these scores right here are tied to this particular iguana. So it may just be that some iguanas stick out their tongue more often than others. So the fact that this lizard one is 30, that might suggest something about how many are in the other ones, and we can actually see that the second lizard 6606 and 13, so not that tonguey. So the fact that this clean sand had 24 and the fact that this lizard sand had 30 are both tied to the fact that lizard number 1 sticks out its tongue a lot. So these are not independent from one another. But if we treat them like they are, and we just do an ANOVA, and we just we use extrusions as our outcome variable, and we predict it based on the type of sand, and we make our what's called model wrong 1, and when we look at our summary, we say, yep, it's significant. But notice our F value and and how it's not right. Then when we move on to as a linear model instead of as an ANOVA, if we do this as a linear model, but again, we're going to do it the wrong way. And so first we'll start to see what its default contrasts are. And we see that the clean sand is the comparison group. So now if we run this as model wrong 2 as a linear model, just regressing extrusions on this dummy coated sand, now we see that the slopes are correct as far as when we look at our dummy codes, this intercept is the mean where all the contrasts are, where everything in the model is 0. Where is everything in the model 0? It's for the clean sand. So in other words, that the intercept is the average of the clean sand. And if we go back and check again, we can see there that our 6.8 is the average, is the mean for that clean sand. Then this slope here is if when this contrast is 1, which is when it's the home sand, and this slope of minus 0.8 means that it is 0.8 lower than the intercept, which we can see here. So this is interpreted the exact way. So you see that these slopes are correct. They give us those group means, but again, notice our degrees of freedom here. This is the 4 and 45 degrees of freedom with an f-stat of 3.9, just like this ANOVA up here. And again, on 4 and 45 degrees of freedom. Whereas when we ran it as a proper repeated measures ANOVA, recall it was 4 and 36 degrees of freedom, and our F value was 8.8. So what's going on here is that we are ignoring that that independence in our data, or the non-independence in our data rather. And so we fix the problem by adding that source of non-independence, by accounting for the subjects within the data. So I'm going to create a factor that from the ID variable and call it IDF. And now we're going to fit 2 models, one that is just the intercept and the slope of that each participant, each factor, or the factor of participants gets a slope. So there will be n-1 slopes, and in this case we have 10 IDs, 10 lizards, which means we'll have 9 slopes for that factor. And that's going to be our compact model, the intercept only and the slopes of that ID factor. Then for the augmented model, we also add in the slope of sand. And then we will compare these 2 models together. And now that we have added in that source of non-independence in the data, we are getting our correct 4 and 36 degrees of freedom, and the F value of 8.8, P is less than 0.05. I did want to point out here, I have a note, just to remind you that in these R models, the 1 doesn't mean the number 1. The 1 means the intercept. And if you want specifically to leave off the intercept, you either have to negate it with -1 or change the 1 to 0. So it's not the number 1, it is a binary number, 0 meaning no intercept and 1 meaning the intercept. You could also, instead of using model compare, you could throw your models into the ANOVA function and it'll give you the same information. But the problem with doing this way, or as far like it works out when you do the model comparison, but what would happen if we looked at just the summary for model C? And you can see the problem with not with the model comparisons here, but as far as like why you wouldn't just look at the summary of even model A. We'll change that because that might make more sense. So if we look at our summary of model A, I would hope that you might intuitively see why it might be a bad idea to have it this way. We have 13 and 36 degrees of freedom, and this is an overfit model. In fact, it's a perfectly fit model because we have a parameter for each and every lizard. And so the reason that we wouldn't want to interpret this model is because we have so many parameters, but it's the model comparison of those two models where we can see that same F-test for the repeated measures that shows us that, yes, there is a significant difference in amongst these groups in this repeated measures design. So in general, for simple, straightforward repeated measures designs, you might find Easy ANOVA to be great. Going forward, there's a much better and more flexible way of doing things, and that's repeated measures are just essentially a type of, or at least they can be analyzed and replicated as mixed effects models with some random effects in there, and we'll talk about that in a minute. But I also did want to point out here that I have this thing that if your repeated measures is a, barely technically repeated in that like there are two measurements, you don't need to treat it as a repeated measures ANOVA, just as a reminder that if there's only two, and whether it's, a pre-test, post-test, or it's just like score 1, score 2, whatever, however you think about it, if it's looking at two scores and only two scores, you can either have your outcome variable, you can regress your second score on the independent variable and a covariate of the first score, and that's likely going to be the way to go. Or you might take a different score and just regress that on whatever your variable is. But point is that you don't need to do a repeated measures ANOVA if there's only two measures. That either one of these two methods will give you the exact same information as if you were to put it in Easy ANOVA, for instance. So the last thing we're going to talk about is looking at the repeated measures as linear mixed effects models. And so this is here just to remind you what Model A was, that it was just extrusions regressed on sand and the ID factor. plus obviously the intercept. So we're briefly going to see this function Elmer, and Elmer is from the LME library, and it is one of the predominant libraries and functions that's used for fixing linear mixed effects models. The way that Elmer, you specify models in Elmer, it's very similar to how you do it in LM. In fact, it's almost identical. The only catch is that when you're doing mixed effects models, what we're talking about is that you have fixed effects and random effects. And so in Elmer, you have to specify your fixed effects and your random effects. So how do you do that? Is you regress your outcome on whatever your fixed effects are, just like you would in an LM model. And then your random effects get specified within a set of parentheses like this, where it is a whatever the random effect variable is, then this bar, which is if you shift and slash, and that's actually called a pipe, and I hate to call it that just because I'm not talking about a pipe, but it's actually the pipe key, and so you have your whatever your random effects are, and then whatever your grouping, your within ID variable is, and specify that. So all we're doing here is we're taking the model is almost the same, except we are saying that we want to fit a linear mixed effect model that has a fixed effect of the intercept plus the slope for sand. And for random effects, we're wanting random intercepts for the ID factor. So we're allowing the intercepts to vary randomly, which essentially means, like I said earlier, this lizard number 1, it just sticks out its tongue more. So its average is going to be higher than the others. So if you fit a linear model for each of these 10 lizards, the intercept of this lizard would be higher than the intercept of this one, because it would be if you fit a separate linear model for each of these lizards, lizard number 1, its intercept would be 32. Lizard number 2, its intercept would be 6.2. This one would be 4.4, etc. So what you're doing here by saying a random intercept, and I keep saying a random intercept because the random effects in this case is only the intercept. It could be, you could add, some other thing here if we had some other random effect to add in. But in this case, all we're doing is we're saying, okay, if we allow this independence, because we allow each of these iguanas to have a different intercept, and after we fit each of their intercepts, then we want to just look at the slopes of sand. So basically ignore where the lines cross, the y-intercept. We just want to know what are the angles of the lines between the groups of sand. So when we fix this Elmer model with extrusions regressed on sand and allowing random intercepts for the IDs, if we look at an ANOVA of that first model that we ran and then the second one, we see that again we get that same 8.81 as our F value, and because this is essentially doing the same thing that we were talking about earlier. The nice thing about Elmer is that once you understand linear mixed effects models, and I highly suggest taking Bill's linear mixed effects model course when it's offered next, But this basically becomes the ultimate, flexible version of the repeated measures. It doesn't matter that, because even if once you understand Elmer, then going into if you need generalized models, so if you're needing to do logistic regressions on linear mixed effects models, it would just be GElmer or Glimmer for the generalized Elmer and things like that. So point is that this expands up, and so this is just like the most basic use of linear mixed models is a very simple repeated measures design. But I do think that Bill plans on lightly touching on mixed effects models a little bit more in the coming weeks, and so we'll likely see a little bit more of this Elmer function, but that will wrap up all I'm going to talk about today. If you have any questions, feel free to reach out or pop in on for drill on Tuesday, and I will talk to you all later.